Have our final afternoon speaker is Moshe Vardi, who's speaking on phase transitions and computational complexity.
So it's late in the day, everybody's tired, so I'll try to be somewhat provocative. Let's see if I succeed in provoking you. So let's take kind of a big look at the area of complexity theory. Started really way back in the 1950s in the Soviet Union, where people studied what they call the problem of Perebour, of brute force search. I always wonder about the language that have a nice short word for brute force search. What does it tell you about the culture? So people there work very hard, but Boris Trachtenberg has written a nice survey describing the work, but ultimately, in some sense, it was not successful until the breakthrough of the early 70s in the West by Cook and Karp, and in Soviet Union by Leonid Levin, that finally provided kind of an explanation for the phenomenon of hardness that we see in terms of reductions and NP completeness, in terms of worst case complexity. Now, people realize fairly soon that there is something unsatisfying about worst case complexity. I'll come back to it. And there was another attempt to address it, again by Levin, and then Yuri Gurevich was a kind of try to promote the theory. This is the theory of average case NP completeness. I have to say, if you force me now to try to come up back with the definitions, I can't even come back with definition. The theory that seemed very powerful, but wasn't too successful, not too much follow-up, very hard to prove the problems are average case NP complete. And then in 1991, there is an AI paper by Cheeseman, Kanevsky, Taylor, with a beautiful title, Where the Hard Problems Are. And again, they argue that worst case complexity is not always the right measure to measure to tell us what's going to happen in the real world. And in fact, SAT is a perfect example. On one hand, SAT is NP complete. On the other hand, we know we can solve problems with millions of clauses, industrial problems, people are solving them on a daily basis. And so Cheeseman et al. Offering another way of looking at trying to say what problems are hard and define some notion of constrainedness. And the intuition is if the problem is very under-constrained, it should be very easy to find a solution. And if a problem is over-constrained, it will be very easy to prove that it's unsatisfiable. But when it's in the middle, that's where the hard problems are. Okay? It's for a paper that talks about the hard problems. It's a very soft paper, but it has huge impact. So it was followed up by people start looking, for example, at free SAT. So let's remind everybody what is free SAT. We have variables, propositional variables. They appear negatively or positively. We call them literal. A clause in free SAT is the disjunction of three literals. And an instance is a conjunction of clauses. Now we're going to look at important parameters going to be the ratio between the number of clauses and the number of variables. The number of variables we'll call the order of the problem. And that ratio between clauses and variables we'll call the density of the problem. In random free SAT, there are various models for random satisfiability problem, but in random free SAT, or more generally random K-SAT, we fix order and density, and then we choose the clauses uniformly. So once you fix the order and you fix the density, you know how many clauses you have to have, and so every clause you simply choose uniformly. And of course, you do with repetition, without repetition, doesn't make a big difference. And asymptotic is we fix the density, and we take the order to the limit. And of course, free SAT is a kind of a canonical NP complete problem, and it's a basic reasoning task. We just heard another talk about SAT. SAT has been enormous industrial success. It also proved to be a beautiful algorithmic abstraction in the sense that people put so much effort into engineering SAT solver that if you have to do something, let's say you want to build an engine for graph colorability, you'll do quite well by simply reducing it to SAT and enjoying everything people have built on top of SAT solver rather than engineering everything back to your own problem. So people start running experiment on random free SAT, of course not at the limit, but looking at larger and larger problem. And here is a typical plot that I found out from Chinese paper, just what I found on the web. And what you see is what happens as you take the density, and here you see the density in the range of between 3 and 6. So the obvious thing is when the problem is the density is very low, the problem is under constraint, you expect to be satisfiable. And so indeed you see that it is satisfiable with very high probability. and when the problem is very dense, it's over-constrained, you expect it to be unsatisfiable. I mean, it's not obvious, the intuition is not obvious why it should already happen in fairly low density. You could imagine you need many more clauses before you get unsatisfiable, but even a fairly low density, it becomes unsatisfiable. Now here's the interesting thing that happens. What happens when we increase the order? So the red is lower order and the blue is higher order. It means as you have more variables, the function becomes steeper. So now you think, okay, what happens if I take it more and more? And people see that the function becomes closer and closer to step function. So this is really the intuition, is that for easy satisfiability, if the problem is under constraint, it will be easy, and therefore we expect in the limit the probability to be 1. And if the problem is hard, we expect the limit of probability to be 0. And so the conjecture is that we're going to have a sharp phase transition, and this is a very tantalizing conjecture, been open for many years. The best numbers that I have, I've just consulted with the expert, these are apparently the best numbers, is that we know that for density below 3.52, the probability is 1. And we know that for density above 4.4898, the probability is 0. And this is like from 3 years ago, and this was a major progress. Before that, it was, for several years, it was open. It was at 4.506. So just this small improvement took several years to get this small improvement. So very tantalizing problem. Now here it gets very, very interesting beyond this fascinating phenomenon of phase transition. What gets to be really interesting, okay, is when we put on the same curve, on one hand, the probability between 0 and 1, 100%, and the other one is running time of some solver. And what you see is what's happening is that for a very low density problem, you will find very quickly truth assignment. And for high density problem, we find very quickly a proof that the problem is unsatisfiable. And you see, where does it take you a lot of time? The peak happens just around the phase transition. So when people saw that the hard problem seemed to be lying at the phase transition, wow, that was very exciting. And so this was a paper, very important paper by Mitchell, Selman, and Levesque from 1992. And they call it the easy, hard, easy pattern. This picture here, easy, hard, easy pattern, that's what they call it. And so empirically, we see, first of all, they say, okay, this a very nice demonstration of the Cheeseman et al. Thesis that the hard problems are at the crossover between under and over constraint. And so we see that we have a phase transition empirically at 4.26. This is the best experiment. And indeed, if you run a DPLL solver time, and this is true, this held true if you run, even if you run CDCL solvers, pretty much you still see the same phenomenon, that the peak is the density 4.26. So the low density is easy, the high density is easy, and the crossover, that's what the hard problems are. Okay? Yes?
So, but this is only visible if you look at the average over satisfiable and unsatisfiable problem. If you only look at unsatisfiable problems, they become as harder.
This is over all problems. This is over all problems. Okay? This is over all problems. So at this point, people really started literally salivating. I mean, you can find the stains on the carpet. So because suddenly we see there seems to be a very profound and fundamental connection between computational complexity and phase transition, where in this case I focused on three sets, on logic, but you see the same phenomenon in other problems. Here's, for example, a beautiful demonstration of this. Take random graph and focus, let's say, on free colorability, okay, K colorability for any fixed K. So again, we'll take the number of nodes to be the order of the problem, and the number of edges divided by the number of nodes is the density of the problem. And we do the same thing. To take a random graph, we fix the order and the density, and we take the edges at random, uniformly at random. And asymptotic is we fix the density, and we take it to the limit. And you run experiments, and you get very similar picture. First of all, you get the step function at some 4 point something. I forgot now exactly where the crossover is for free colorability. And you see the same easy, hard, easy pattern. And here it gets even more beautiful. For two colorability, probably there's no sharp phase transition. Yeah.
Would
Who said there is?
Just a minute, wait a minute. For two colorability, probably there is no phase transition, and for three colorability, empirically there's a phase transition. And what else? What other proof do you want? There is a profound connection between phase transition and computational complexity. So the 1990s were, I would say, the people were all agog over this. Of course, the physicist says, well, phase transition, we know about phase transition. This is all about some solid physics. We are experts on phase transition, spin glass, and there are lots of papers in physics written on it, articles appearing in Science, lots of invited talks. Microsoft formed what they call a theory group, where basically they say, we're going to use statistical physics to solve the P versus NP problem. It's fair to say careers have been made based on this inviting possibility of the connection between complexity and phase transitions. Now, as was pointed out, there are already from the beginning people realized there are problems. The basic problem is nobody was really able to prove anything about phase transitions and complexity. I mean, if you look, for example, what did people do in Microsoft research? For example, they study how the step function, how fast does it become steep. Okay, very nice result about how fast the window narrows down. If you take any kind of two distances, probability 1 minus epsilon and epsilon, how quickly is it going to narrow down? But nothing really about complexity theory. Also, already in 1992, Schwarzschild and Gere proved that 2SAT, annoyingly, has a phase transition. And in fact, several years later, in 2000, XOR-SAT, which is essentially linear equations modulo 2, and because it's linear equation, it is in p time, also have a sharp phase transition that is probably at density 1. Okay? So we problems are tractable and they still have a phase transition. And I'll give you another example of that, something that I was involved with, and this is Horn-SAT. So Horn-SAT is you have clauses, and every clause has at most one positive literal. And this is a classical result proven, discovered more than one time, that this is not only in polynomial time, but this is with linear time, satisfiability is in linear time. Very easily solvable. And so together with my student Demopoulos and Chris Moore and Gabriel Istrate, we looked at the model we call random 1-3 SAT. So we fix one negative clause, one negative literal, and then we have two parameters, one for how many positive unit clauses you have, and so we choose them uniformly at random, and then how many, this implication, PQ imply R, 3 clauses you have. So you have two different densities. So we call it D1 and D3. So you actually get a two-dimensional terrain, and we discover there is a phase transition. Actually, it's even more interesting. There is a region where there is a phase transition, and then there is a region when there is no phase transition, and the transition between them is sharp. So there is a second order phase transition. So there's a beautiful kind of combinatorics, but this is a tractable problem. So you can always look at this and say, it's not clear there's really a deep connection between phase transition. Phase transition clearly do not imply computational hardness. I mean, it's a little bit like when you go to the doctor and you say, I have a back pain. Doctor sends you to do an X-ray and they say, oh, you have a bulging disc. So somebody decided to do an experiment and took just a random sample of the population and find out that many people have bulging discs, and there's no correlation between that and pain. It's just not an explanation, it's just a phenomenon. But the problem with the story with the phase transition goes even deeper. So in a paper with a bunch of people at Rice in 2000, we went back even to this basic story of easy, hard, easy. And the question is, what does easy and hard mean in this story? Yes, it means I see a bell-shaped plot. But what does it mean? And where do you see the transition? What does it mean there is a transition there? So if you go back and you look at the Mitchell-Selman-Levesque paper, what they're doing, they're fixing the order and they're varying the density. And as they do that, you see the bell. But actually, we have pretty standard definition in computer science what easy and hard means. And that means easy means polynomial scalability. You get a bigger problem, and it should scale polynomially. That's what we mean by easy. And hard should mean exponential scalability. This is pretty standard. And that means that they've been looking at the wrong way. they should have been fixing the density, and then they should scale the order. Not fixing the order and scale the density. And this, first of all, corresponds to the way we analyze hardness of problems. It also corresponds to applications. For example, one of the things that you do, if there's something called bounded model checking. Bounded model checking, you take the circuit and you kind of unroll it a number of times. As you unroll it, the density doesn't change because the density is essentially a parameter of the circuit. The order changes, the density is fixed. So doing this way makes a lot of sense. So that's what we did. Okay, here it is. So here you see, so why this a 3D plot? So on one hand is the density, you see between 0 and 15. And on the other dimension, it's the order. We go from 0, in this case, 250 variables. And the height is the running time. And this is log scale. So this is, you should think of it, this is really going way, way up, okay? This is log scale. So what you see is that the easy region is easy, okay? I mean, kind of flat. You see a peak, indeed, around 4.26. You can exactly see where the peak is. But see that the other, even after the peak, it's kind of straight line. And straight line should mean what? It's really exponential. And in fact, here is what happened when you run it on a density 3.7. This is a linear scale, and what you see is a quadratic scaling. But when you go to 3.8, you get exponential scaling. So already in the satisfiable region, 3.8, what you're quite far from 4.26, every solver that we threw at the problem was scaling exponentially. So we got a very different view of instead of the easy, hard, easy, we get a very different view. So below density 0.8, it's really easy in the sense that standard solvers seem to be able to solve the problem in polynomial time. Median, I mean, one has to remember, but this is kind of built in. This is average of median running time. And so this is not instance by instance. Between 3.8 and 4.26, these are actually hard problems, and they get harder as you get closer to the phase transitions. Okay? The exponent, the coefficient, the exponent gets higher. After 4.26, it's still exponential, but the exponent is declining. So we call this easy, harder, less hard. And so now it seems that there are actually several phase transitions. So a density, this was known before, this was shown by Fries and Apfel before. Density 1.63, there are some algorithms that guarantee to solve the problem in fact in linear time, up to density 1.63. So we know, and then these algorithms are not correct anymore after that. So you can think of it as some kind of algorithmic phase transition. The algorithm stops being correct at some density. And then something also happened at 3.0, another one, the pure literal. The first one, the pure literal rule. The second one, I forgot, this is Fries and Suen. And then we see some kind of a transition between at 3.8, that problems that solver are polynomial, and then they become exponential. And then there is a probability transition at 4.26. So there seem to be actually not one phase transition, but at least several phase transitions going on. Now, as you see, part of it is analytical, part of these results are empirical. So there is a question, is there any theory behind it? And there's an attempt to develop a theory behind it, and it's called algorithmic barrier theory. So what is algorithmic barrier theory? So the algorithmic barrier theory said, let's look at the solution space. So we have n variables. So every assignment is just an n-bit vector. So we can define the obvious thing, think of it as a hypercube. So adjacency between two such bit vector means the Hamming distance is 1. So they agree on everything except one variable. And then you can look at this graph. In particular, you can look at connected components of the graph, and they are called clusters. And Achlioptas and Koja Oglan in 2008 said, first of all, for low density, below 0.163, there is a single cluster, and that kind of explained the previous algorithmic result, saying why the pure literal rule actually would work below that density. Then they break down into some number of components, and there is a density. They give better. They are able to give sharper result for higher k, for k satisfiability. For 3 sites, it's a bit hard to pinpoint. But even that, we know there is a density where the space of solution, this is interesting, Freudian typo. It's meant to be shattered with A. And it came up here, I don't know what it means. But shatters into, breaks down into suddenly exponentially many small clusters. So something does happen. If you look at the space of solution, it suddenly crashes, shatters into many such unconnected clusters. And they argue that this provides an intuition the algorithm are stopped being effective after the shattering point. You can think the window of opportunity shatters, and the algorithm don't work anymore. So that's what they call the algorithmic barrier theory. Except there is a big flaw here, that if you go to XOR SAT, and you look at the same structure of solutions and the same graph, you also see the same phenomenon, shattering. In fact, that played a key role in the episode of about a year and a half ago, when Deo Lalikar announced that he has a proof that P is different than NP. And his argument was, using logic, using the Immerman-Vardi theorem, you end up that if 9 SAT is in P time, then it can be expressed in fixed point logic, and from this it would follow that there is no shattering. That's essentially what he was claiming. And so this was the argument, therefore, that 9 SAT cannot be in P time. And people noticing that the same argument would prove that 9 XOR SAT does not shatter, but we know that it does. People prove formally that it does. So this actually played a key role, the shattering result for XOR SAT.
So how come the Mazard-Ricci paper is earlier than the Cleopatra paper?
It's about XOR SAT.
So they proved, so they had this idea of shattering, and they showed that XOR SAT.
They showed the XOR SAT shatters, and the good questions. Why? How can Achlioptas and Koja-O'Gallan claim that this explains intractability? And in fact, Achlioptas was one of the people who immediately said, no, Deo Lalikar is wrong because XOR SAT shatters. So one of the things we know about, for example, about XOR SAT, it's in polynomial time, but if you throw a normal solver at XOR SAT, it will not solve it efficiently. If you write a problem, you have to have a special solver to solve XOR SAT efficiently. And in fact, we know that BDD-based algorithm can solve XOR SAT efficiently. And so part of the experiments that we did in 2000 were also using BDD-based algorithm. But we looked at them in just normal 3-SAT, okay, random 3-SAT. Now look, this is a terrain. Now remind you, we had before that we saw the terrain that there was the ridge, and then you go down. How is it different here? Everything is much steeper. We go up much faster. We fall much faster. But the peak is not at 4.26. Now the peak is a density 2.3. Not only that, at a very low density, 0.2, we have quadratic scaling. At density 1, we have exponential scaling. So we see the same phenomenon, easy, harder, less hard, and we see a shift between polynomial and exponential scaling. But it's happening completely different numbers. This is all empirical. It happens completely different numbers. Now this is a completely different solver. It's not based on search, it's based on constraint propagation, where you present the constraints using BDDs. So what can I conclude from this? One is that, in my opinion, the easy, hard, easy, it's just completely wrong. It was wrong all along. And I would say that the easy, harder, less hard seem to be a more accurate picture, but I can't even claim that this is a fundamental pattern. In particular, it seems to depend on the algorithm. The low density is one thing you can say, low density problems are easy. We can say that with certainty. But we cannot say, it's a big question, are the high density problems. We know they're hard for resolution based, they're hard for resolution, therefore they're hard for all resolution based solvers. But we really don't know that they're hard. I mean, XOR SAT is going to be hard for resolution based solvers, it's just not hard for other solvers. So we really don't know that the hard problems are hard, even though they're hard for us right now, for most solvers. And so far as I can say, there is no evidence of intrinsic hardness. There's evidence of intrinsic easiness. But there's no evidence that there's any connection really between phase transitions and computational complexity. The story was just a beautiful story, just a bit too good to be true. And that's the end of the story.
So have you looked at SAT instances obtained from cryptography and tried to empirically find whether there is a... So I have lots of cryptographic examples for you.
Yeah.
These are obtained by translating MD5 and MD6 inversion problems into SAT problems.
Mm-hmm.
And what's interesting is that we already know they are satisfiable.
Right.
The question is, can you find a satisfying assignment?
Right.
Right?
And they're hard, right?
Very hard.
Right.
So I tried running my SAT solver on it, and when you have the MD, this was because Ruvest wanted his MD6 to be kind of empirically tested.
Yeah.
And he has some proof of why it is difficult to invert and is collision resistant. So now the question is, so you run this MD6 algorithm, 16 rounds, 17 rounds, 18, 20, all the way up to 80 rounds. And as soon as you hit 15 or 16 rounds, up to 16 rounds, it's very easy to solve these instances. After that, it's like suddenly becomes hard. No idea why. It could be interesting to see if there is a similar phase transition in the context of ordered. You measure the density in the same way that you're measuring and increase the order somehow. And
so we do know we have enough analytical result, at least if you go on the simple random 3-SAT or random k-SAT, that as you're changing density, just the geometry of the space of solution does change, and there are several phase transitions. The question is, how does it affect, what's the algorithmic impact of that? So it does seem to affect specific algorithms.
right.
Okay, so it does seem to be, for example, that it could very well be that the chattering does affect DPLL or CDCL type algorithms. It just doesn't affect other algorithms. So there's probably is a connection between structural properties and how specific algorithms behave. But to go from this and to say there is intrinsic complexity, that's an argument I think there's simply no evidence for it.
Perhaps I can also, before coming to my own question, making a remark on that. So I call it, so you said, so to speak, you found this phase transition for 3-SAT and 3.8, so to speak, so this other phase transition. Actually, with my experiment with other solvers, I already got this from polynomial to exponential at this density of 3.2 something, which was computed by Archioptas. So, but it seems to be, so as soon, so to speak, you hit an unsatisfiable problem, since you can only solve it in this, if you always guess it. But as soon as every unsatisfiable problem, I've also made a conjecture, I think there are some partial results on that. So every unsatisfiable problem is hard. However, you can avoid it, so to speak. The task is to avoid to go into this unsatisfiable problem. And I think this is also for these cryptographic problems. It's very similar, since you can just analytically also solve some of these low rounds, certain ciphers, so to speak. Then you see, so to speak, this propagation, and so it all goes through, so to speak. You never hit an unsatisfiable problem. But as soon as you really hit an unsatisfiable problem, then poof, so to speak, this is kind of explosion.
I mean, naturally, once you have an unsatisfiable problem, there is a chance that you have to spend a lot of time, trying to prove it's unsatisfiable.
It seems like a probability that you hit these unsatisfiable problems.
And so one of the things that we do know is, even if you take a satisfiable problem, there are so-called frozen variables. So you make one wrong assignment, and now you end up with an unsatisfiable instance. You spend a lot of time proving it's unsatisfiable, backtracking. You flipped it one variable, and then you find a solution. Yeah.
But in the case of cryptography, we don't have unsatisfiable
formulas. Sub-instances.
No, they are all satisfiable.
But you may have frozen variables. So you run into unsatisfiable instances, same way. You make one wrong assignment or a few wrong
that's
assignments,
true.
then
That's
you end up with unsatisfiable instance.
Yeah, that's true. But the problem itself in general is always satisfiable. The question is, can you break it?
Yeah.
Okay. We take a question from someone else.
The more interesting, MD5 and MD6 are slightly more complicated, but the more interesting ones from cryptographic graphic point of view is the stream ciphers, because a number of stream ciphers over the last 10 years have been broken by SAT solvers or by reducing the equations. And trying to understand what stream ciphers you can't solve by just throwing a SAT solver at them is kind of interesting design criteria which is really interesting.
So I think understanding which instances are hard and which one are easy, develop relative, not intrinsically, in my opinion, but relative to a class of solvers that we are running. I think that's a fabulous question. I mean, I think our theory is just too poor right now. So it's NP-complete. But in this NP-complete, there are some very hard problems and there are some easy problems for us. And we have no good understanding of when is it hard and when it's easy. So I think finding good explanation for why certain solvers are having a hard time or easy time with particular problem, I think that's a really very important question. But one has to be very careful from anything you say about a specific algorithm to make some claims about intrinsic hardness. Oliver?
So this just another facet on this about phase transitions or no phase transitions. If you now consider it from the point of view of proof complexity, here then we just want to unsatisfiable 3-sat, random 3-sat. Okay, so there's this proof, so to speak, that above the threshold they're exponentially hard.
Right.
Also, I have a conjecture, and also tried experimentally. So the density is the hardness of unsatisfiable problem is completely independent of the density, except of perhaps a very low density is below 1. But so it goes up, so to speak. It's only they are becoming don't find them. But so if you now condition on unsatisfiable instances, then I could go up to 3.8 density. Of course, I had to run a lot of time, but they're becoming harder and harder. So it's only our proof technique. Actually, the proof techniques they break down. They need the.
So what you're saying essentially that unsatisfiable problems are always hard.
Yes, yes.
At least for resolution.
For every
Yeah.
random problem.
Yeah.
So there are actually provers which do work on unsatisfiable things up to certain density, which is lower than the critical one from resolution. The probability going to 1, they will find a short proof. And this is even a subset of the ordinary textbook propositional calculus. But it's stronger than
Only from the other
resolution.
end.
Yeah,
Or
it's
high density.
behind the conjecture threshold, it's in the range of unsatisfiable formulas, and they are still easy for some time. To density something like n to 1.4, I think. So,
I mean, we don't even know. I mean, there is a conjecture, right? That the question is even for resolution. Right now, the bound is like 5.2, I think. We know about 5.2. It's
that's
where
for
it's
resolution, but for this, the success is actually lower than that.
lower than that. But we don't know whether the 5.2 should be able to push it down. In fact, Oliver, he believes that even below the satisfiable region, below the threshold, if it's unsatisfiable, it should have hard proof
Well,
complexity.
but that can be specific only to resolution. It's
No,
not
right,
a
right.
phenomenon about some
Yeah.
kind of.
Yeah. But essentially, all SAT solvers today are based on almost all SAT solvers are based on resolution. Okay, thank you very much.